We have a 4-point plan left. We talked about statistics, but we didn't really do it. Now we're going to do it. Hypothesis test and confidence intervals for the intercept and for the slope. So we're going to use the formulas that I showed before for what we now are going to call the standard errors or the sampling uncertainties of intercept and slope. I mean, we can do it for both. Everything can be done for both, but I repeat to you, usually the slope thing is the more interesting thing to look at. The other thing is often not so relevant. But it could be done if it is. Now this is a bit confusing because we have two zeros and ones here. We both have 0 and 1 for intercept and slope, and we have 0 and 1 for the null hypothesis and alternative. So it's really difficult to understand this. But hey, maybe we should just understand it. There are both a null and an alternative for both the 0 and the 1. Right. That's the thing. We can test specific values for the slope. Let me focus on that one. We can test a specific value for the slope by comparing the specific hypothesis value with the computed value, exactly like we did for the mean a few weeks ago. The observed mean subtracted by the hypothesized value of the mean. Divided by the correct variability measure, that is the sampling standard deviation of whatever we compute. In this case, the sampling standard deviation, the standard error also called, of the slope of beta 1. And the way we do, and now you're a bit up and going now, having told you that the distribution that is relevant for us to use here, which the theory tells us, is the t distribution. Now with n minus 2 degrees of freedom, not n minus 1, but n minus 2. Knowing that, everything now runs as a few weeks ago on the means. We can do hypothesis tests, and we can do confidence intervals. Let's try. Let's specify the confidence intervals first. For instance, it's expressed as a method 514, and let me again focus on the slope. The confidence interval of the slope comes from the computed slope plus minus the t percentile, as we've seen before, using the right t distribution, times the right standard error. We've also seen that before. For the mean, we plugged in s over root n. That was the right standard error. That was the formula for a one-sample mean. Now, the right standard error has a name, and it could be computed by the formula that I gave you, or it can be read off in R, as we've already seen, or the formula, as I said, right? So we use those formulas, or we can read them off in R. This is where I'm going to jump to R and rather have a look at the result than the simulation illustration I was bringing on my slides. Let me go up in the beginning, and I do my height-weight thing. My height-weight thing. Let me just look at the result here. This is the result I also showed you on the slides in the beginning. Here I now computed them in R again, right? Slope, intercept, under the heading of estimate, standard error, under the intercept, the standard error for the slope, that's the interesting thing, right? It's 0.1 cent, it's 0.1 kilogram, sorry. 0.1 kilogram is the uncertainty on the slope. So we could, that is the sigma hat beta 1, this number, right? So I could read off this number, and then I could combine it with the t percentile, and then get the confidence interval. The confidence interval is actually not explicitly spit out to us in this summary. Could be by other means, but not in this summary. And then it gives us a hypothesis test also, which, and this is something we need to know, the hypothesis test given to us by default, by such an output here, it gives a t-value of 10.50 for the slope, and it gives a very, very small p-value. The hypothesis test, which is tested by default, is whether the slope could be assumed to be 0. Right? Hypothesis, slope is 0. Alternative, not 0. Hypothesis, no relation between x and y. Alternative, there is a relation. Right? P-value, very, very small, so we reject the null hypothesis of a 0 value of no relation, so we have proved, not surprisingly, given the data we're looking at, of course, but statistically now, we have proved that there is some relation between x and y in this case. We have made very strong evidence against the idea that there could be no relation, the null hypothesis. We have proved the null hypothesis of no relation wrong by this small p-value. That's the interesting thing. And we could then quantify it by taking 1.111 plus minus the t percentile times this number, and we get a confidence interval. This slide I'm going to skip. It's just, in a way, it's not because it's not interesting, but I think you can play around with it yourself if you want. It's trying to show to you that if I repeatedly do confidence intervals, they include the true value. If I do a 95% confidence interval for the slope, it will include the true slope value in 95% of the time. I could check that by simulation. That is what is done here, right? So let's not do that. Let's move on instead to the next and 6th point of this regression stuff. Now I told you